set up delta G. Delta G of formation.
Okay. Did we calculate the delta G yet or not?
Only the first part because we could just go through it. We have very little.
All right, so the reaction that we were looking at was N2 plus O2 yields NO. We'll need 2 of those. These are all gases. And we want to find out what delta G is under standard conditions at 298 Kelvin. So the easiest is to use delta G's of formation. And so did I write down the delta G's of formation? I think the delta G of formation under standard conditions for N2 is 0. I think we've got that far. And this is 0. And what was the NO delta G of formation? 86.55? Okay, thanks. Kilojoules per mole. And so we take that, the sum of the products minus the reactants. The reactants are all 0. So the product is, we have 2 moles of this, so we'll have to double that. The delta G of formation is only for 1 mole, so this is actually twice the delta G of formation of NO. This is a formation reaction because we're forming NO from the elements, but it's twice a formation reaction because we're not forming 1 mole, we're forming 2 moles. And so we have to double this, and so delta G for this reaction is going to be 160, 172, 173.1. Actually, we're only allowed 4 sig figs. Just say 173.1. All right, 173.1 kilojoules means it's pretty unfavorable. And so if we have a delta G of that magnitude, what is our K value looking like? Oh, actually, before I get too far, I need to do one thing. So if our delta G is plus 173, we're getting up there. You know, this is looking like it's between 10 to the minus 18 and 10 to the minus 36. Closer to 10 to the minus 36, right? With a K value that small, this is heavily favored towards the reactants. And so we're getting into the no reaction territory up here. It's plus 173. But we can go ahead and calculate what that K value is. So let's go ahead and do that. But before I do the calculation for the K value, I made a change to the homework here. And so the change is, I'd like you to do, you can cross out, this is 72, 78. I'd like you to do 73 instead, 74, 75, 76, 78, and 90. And just eliminate those last 6 problems. This is for chapter 15. I'll post this on Canvas as well. And so there's a change to the chapter 15 homework, just the last 6 problems. All right, so what we're going to do is we're going to figure out what K is. So I know it's going to be quite small. And so K, we could just use this. K at 298 under standard conditions is going to equal E to the minus delta G under standard conditions at 298 divided by RT. And so we'll go ahead and plug this in. This is going to be equal to E to the minus delta G under standard conditions. So this is going to be minus 173.1 kilojoules divided by R, which is 8.3145 joules per Kelvin, divided by T, which is going to be 298 Kelvin. This is the temperature we're doing this at. Now the joules and the kilojoules don't cancel. And so I'm going to change the kilojoules to joules. So 1,000 joules per kilojoule. And so let's see what this comes out to. Okay. I'll have to use my phone calculator. So it comes out to negative 173,100 divided by 8.3145 divided by 298 equals, and then E to that answer. And I get a K value that is 4.561 times 10 to the negative 31. So extremely small. And that's the ratio of products to reactants. So it's pretty much all reactants, very little product. And so it comes out to 10 to the negative 31, which is kind of what we were expecting because, plus 170 is going to be closer to plus 200, like 10 to the negative 31. Equilibrium favors the reactants with such a small ratio.
Professor?
Mm-hmm.
The equilibrium would favor the reactants because the reactants are a lot more stable and require a lot less energy to become their molecules, correct?
Yeah. In this case, the equilibrium is favoring the reactants, which is a good thing because air is a mixture of nitrogen and oxygen. And if this equilibrium were favored to the right, then everybody would be breathing toxic NO gas. But fortunately, this equilibrium is heavily favored to the left. And so what does that mean? How much NO gas is in this room? Because we have nitrogen and oxygen in this room, and we're pretty much under standard conditions. Standard conditions is visually 1 bar. And we're at room temperature 298 or close enough. So how much NO gas do we have? Well, when you look at delta G, it's hard to tell. The delta G is just telling you it's unfavorable. Delta G is greater than 0, and it's a lot greater than 0. A better idea would be K, but K still isn't telling you. And so what we're going to do is we're going to do Chem 1B stoichiometry now. How much NO are we actually breathing, if any, in this room? And so let's go ahead and do the stoichiometry for this. So we're going to do Chem 1B stoichiometry. In Chem 1B stoichiometry, we set up something called the ICE table. We talked about before, where I is equal to what? Initial. I is equal to initial. And initially, we're under standard conditions. So if initially we're under standard conditions, then that mean that nitrogen, which is a gas, is at what pressure?
1 bar.
1 bar. And oxygen must be at what pressure? Well, it's under standard conditions. This is also 1 bar. But NO is the product. We'd like this to be 0, but when we do things under standard conditions, it's weird because everything has to be at 1 bar. That is, all the gases have to be at 1 bar. All the solutions have to be at 1 molar. So in order to make this under standard conditions, we have to have product in here. You know, standard conditions dictate that. But if we were actually trying to make it, there's no way we'd want to have to add product, because that's what we're trying to make. We're trying to make the product. The reason we do this is otherwise we're going to have too many tables. And so if we're going to do standard conditions, then everything has to be at standard conditions, and then we can use this table. But if some things aren't under standard conditions and other things are under standard conditions, and then each situation's unique, and we'll have to figure it out. And so to make it under standard conditions, I need this product in here at 1 bar. Now, the direction of change we have to figure out. In this case, this equilibrium constant, K, heavily favors the reactants. And so I assume the change is going to go backwards, you know, here. But I can't always assume it. Instead, what we can do is we can figure out the direction of change by calculating Q initial. We calculate Q. Q is just what we're given. And so in this case, it would be the partial pressure of the products, initial, over the partial pressure of the reactants, initial, raised to whatever power they're raised to. And so for our particular reaction, Q is going to equal the partial pressure of NO initial squared divided by the partial pressure of N2 divided by the partial pressure of O2. Both of these are going to be initial. That is what's given. So for us, the initial NO is 1 bar, or 1. And so this is 1 squared over 1 times 1, which is just 1. And then we compare this with K. Did I already talk about this, or have I talked about? So, if our given or initial ratio was equal to our equilibrium ratio, then there's no change. And so our initial ratio might already be at equilibrium. If our initial ratio were too big, that is, we have too much product, then the change is to the left. If we have too much product, we got to make the ratio smaller and lose some product, make more reactant. Or if our initial ratio were too small, we don't have enough product. And so the change is going to be to the right. And so what we're doing is we're comparing Q, which is 1, and our K. Our K value is 4.561 times 10 to the minus 31. I'm ignoring sig figs for right now. And that shows that Q is much larger than K. We have too much product. And so the change is going to be to the left. All right, if the change is to the left, that means we need to get rid of product. So we're going to have minus 2x here. and we need to gain reactant. So this is going to be plus X. This will be plus X. Bar. 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 How much we have to gain and lose depends on our final ratio. This is our final ratio, so we're going to use that final ratio to figure out how big X has got to be. So this is going to be 1 plus X bar. This is going to be 1 plus X bar. And this is going to be 1 minus 2X bar. So now I'm going to leave a little bit of space here, because once we find X, what X is, then we can calculate all the concentrations here. But we have to solve for X first. And so let's do that here. I'm going to solve for X. And so we know that K is going to equal the partial pressure of NO at equilibrium squared divided by the partial pressure of N2 at equilibrium divided by the partial pressure of O2 at equilibrium. And so the partial pressure of NO at equilibrium is just going to be 1 minus 2x. We don't know how big 2x is. But we're going to have 1 minus 2x. This is going to be quantity squared. The partial pressure of N2 is 1 plus x. And the partial pressure of O2 is 1 plus x. So we'll just take 1 plus x and square the whole thing. And this has got to equal the ratio. The desired ratio is 4.561 times 10 to the minus 31. 4.561 times 10 to the minus 31. And so probably the easiest thing to do here is just take the square root of both sides. So the square root of 4.561 times 10 to the minus 31 is 6.75 times 10 to the minus 16. So simplifying this, I'm going to get 1 minus 2x is equal to 6.7535 times 10 to the minus 16 plus 4.561 times 10 to the minus 31 x. And then I'm going to add a 2x to both sides and subtract a 6.735 times 10 to the minus 16 from both sides. So over here I'll get 1 minus 6.7535 times 10 to the minus 16 is equal to 2x plus 4.561 times 10 to the minus 31 x. So this 1 minus 6 point this is going to equal 0.999 15. I get 15.9. 3, 7, 8, 9, 10, 11, 12, 13, 14, 15. And this is going to be 2 point, and then I'll need 30 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 30 zeros, and then 4, 5, 6, 1, x. And so why don't you guys go ahead and calculate this. See what you get. So I'll get 2 plus 4.561 times 10 to the negative 31 invert that.
Professor,
Uh-huh.
at the top of those three equations, the 1 minus 2x equals 6.7535 10 to negative 16. Plus, would it be plus the same value? Plus 6.7535 10 to 10 to negative 16x? Would that be the case, or why did the square root not apply?
Oh. Over here? Right here?
Yeah, that should be the same number to the right of it too.
Oh, you're talking about this?
Correct.
Um,
Or am I wrong?
yes, you're right. I screwed that up. All right. So let me try this again. So what I'm going to do is I'm going to do I'll do the left side first. 1 minus 6.7535. 6.7535 times 10 to the minus 16. Divided by 2 plus 6.7535 times 10 to the minus 16. Okay, did you get an answer? Did you get an answer?
Yeah.
I'll try it and see what you get. So did you guys get the answer? Same answer?
Yes. We got x equals 0.5.
You got x equals 0.5? Is that what everybody got? Well, if x equals 0.5, then let's go ahead and plug that back in here. What we get is this. 1 plus 0.5, that's going to give us 1.5 bar. And we'll have 1.5 bar here. And then we'll take 2 times 0.5 is going to give us 1. So 1 minus 1 gives us 0 bar here. And so we're going to end up at 1.5 bar, 1.5 bar, and 0 bar. And then what we do is we do a double check. The way we do a double check is we plug the numbers back into K. So it's going to be the partial pressure of NO squared, so this is 0 squared, divided by 1.5 bar on the squared. We drop the units because K's are dimensionless, so activities are dimensionless, and so we end up with 0. And then we compare our two Ks. We compare the K that we get from our calculated versus the K over here, what it should be. So we got a K value of 0. The K value is supposed to be 4.561 times 10 to the minus 31. What's our percent error in the K value? What would be the percent error? Huge. What happened? Our final equilibrium concentrations have to be in the correct ratio, and this doesn't appear to be in the correct ratio. The correct ratio is 4.561 times 10 to the minus 31. We got a ratio of 0. So something went wrong in our calculation. And so let me tell you what went wrong in our calculation. What went wrong in the calculation is your calculator. It's your calculator's fault. What's that? It rounded it, yeah. If you have a standard calculator, the standard calculators now carry 10 digits. And so they figure 10 digits is enough for most calculations. So let's round this to 10 digits. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I round this to 10 digits, then it's going to come out to, your calculator can't carry that. And so it's going to drop the 9 and then round it up. It's going to round it to that number. And so we call this round off error. Round off error is common when we have a large change. So for example, let's say there was a 99.9999999% change. If your calculator can carry this many digits, and my phone can, but my calculator can't, then it'll leave it like this. What's going to happen often is that rather than showing the very, very small change, it's just going to round this to 100%. So what do you need? Well, you need to buy a better calculator, maybe. Will that work? Or we need to do this trick. If this happens, we try resetting the initial conditions. So what I mean by resetting the initial conditions is like this. let's say there's a seesaw and it's tilted to the left. Eventually it'll reach equilibrium, and the equilibrium for the seesaw is just going to be level, like that. So this is reaching equilibrium from the left here. But what if we approach the equilibrium from the opposite direction, that is from the right? So somebody pushed it down here. Would we get to the same equilibrium? And the answer is yes. We'll just get to the same equilibrium. And so it doesn't matter if I approach the equilibrium from the left or I approach the equilibrium from the right, I'm going to achieve the same equilibrium. Does that make sense? It turns out the equilibrium that we're looking at, and so this will be another analogy here, is heavily favored towards the reactants. So let's say I had 1 million gallons of water. And what I'm going to do is I'm going to place all 1 million gallons of water on the left side. And over on the right side, there's no water. And then I let this go, and when this goes, then I'll end up with, let's say I end up with some scenario like this, where I have 999,999 gallons on the left and 1 gallon on the right. And so what we're going to see is a change. And this change is going to be a small change, because out of that 1 million gallons, only 1 gallon goes over to the right. And so it's quite a small change. And then we're at equilibrium. But what if I did the opposite? What if I put all 1 million gallons on the left side of this? So I put all 1 million gallons over here, and the left side's empty. And so what we're going to have is we're going to have a very large change here. Because in this very large change, 999,000 gallons will have to drain it out to the left. And we end up with the same equilibrium. So as long as we start off with 1 million gallons, it doesn't matter, right? It doesn't matter if we start from the left or start from the right. It's just like this seesaw. It doesn't matter if we start from the left or start from the right, we're going to reach the same equilibrium. Well, the same thing here. I just have to make sure I don't lose any water or add any water to it, and then I should end up at the same place. The problem with large changes is round-off error. So what was a percent change here? So that's 1 divided by 1 million. I should be able to do this in my head, but sometimes. Times 100. Actually, this would have been easy to do. This is a 1 times 10 to the minus 4% change. up here, this was a 99.9999% change. So in this case, your calculator will have no problem. You know, we could have done it either way. We could have done the, oops, this is a small change. It's backwards, right? Sorry. But as the percent change gets larger and larger, then we have this problem with rounding because your calculator can't handle that. And so here, they can easily handle it because this would only be 1 sig fig. Over here, you're already looking at 1, 2, 3, 4, 5, 6 digits of your calculator. You only have 4 more left. Here you have plenty left. And so what we're going to do is we're going to try to redo the calculation by resetting the initial conditions. And we'll take a look and see if your calculator can handle this calculation now. So we have nitrogen plus the oxygen goes to 2 NOs. Now the original standard initial conditions were 1 bar. Let's just say exactly 1 bar. This is 1 bar. This is exactly 1 bar. This is under standard conditions. But what we're going to do is we're going to reset it. We already saw from Q that we have too much product. The Q is way too big. And so what we look at is we look at the limiting reagent and we assume 100% reverse reaction. This is like the water. So now I have water in both places, but what I'm going to do is I'm going to push all the water to the left side. And that's assuming 100% reverse. And so this is going to be what we call minus 2y, where 2y is 1 bar. This is minus 1 bar. This is going to be plus y, which will be plus a half a bar. And this is going to be plus y. This is going to be half a bar. So our new initial conditions will be 1.5 bar, 1.5 bar, and 0 bar. So what I did was I just moved all the atoms to the left side. All the atoms are still there. They're just moved to the left side. Okay, now the change always goes to the side with zeros. So we see that we have 0 here. We've got to have something here for the ratio to get the correct ratio. And so the change is going to be minus x bar here, minus x bar here, plus 2x bar here. And so that at equilibrium I'm going to have 1.5 minus x bar, 1.5 minus x bar, and 2x bar. Okay, now I'm going to solve for x. We know that k is equal to 4 0.561 times 10 to the minus 31. 4.561 times 10 to the minus 31. That means most of the water is on the left side. So if I put all the water on the left side, there should be a very small change to the right side. And so that should be good. And so let's go ahead and solve this for x. And so it's going to be the NO squared, which is 2x quantity squared, divided by 1.5 minus x for the n. 2 and 1.5 minus x for the O2, so I'll just square that. And then we'll do the same thing. We'll just take the square root of both sides and then solve for x. So the square root of 4.561 times 10 to the minus 31 I had up there earlier. That was 6.7535 times 10 to the minus 16. Is equal to 2x divided by 1.5 minus x. All right, why don't you go ahead and solve for x for me? Tell me what you get. I forgot to record that, but all right, so we reset it so that the change was small. There's another reason for resetting it so that the change is small. Or if initial conditions is already resulting in a small change, you can use this as well. If I is already resulting in a small change, then we're going to try this other trick. This other trick is called the simplifying assumption. The essay. The simplifying assumption is like this. Let's say I start off with 1.5 bar and I lose a little bit. And the amount that I lose is very, very small compared to 1.5 bar. And so I'm going to say that x is much smaller than 1.5 bar. Then 1.5 bar minus x bar is just going to be about equal to 1.5 bar. And so that's going to make the math a little bit easier. So we're going to apply the simplifying assumption to the last problem. All right, I guess that disappeared. I think I'll have to write it again. In Chem 1B, we have these reversible reactions, so I'm going to write 2 arrows like this. And so we reset the initial conditions, and we got this. This is 1.5 plus x, or no, minus x. 1.5 minus x bar. This is 1.5 minus x bar. And this is plus 2x bar. Should be 2 NOs here. So we're going to get 2x over 1.5 minus x. Now we haven't calculated x, but we're going to assume that it's small because of k. It's very small, so we don't expect the change to be very big. We don't expect to make that much product. And so what we're going to say is that initially we started off with 1.5, and then we're losing x. So compared to 1.5, x is very small. But the 2x we keep, because compared to 0, 2x is significant. And so we're going to apply the simplifying assumption, the SA here. The SA is just going to assume that x is much, much smaller than 1.5. This is even before we know what x is. And the only reason we're going to take that guess is because of the k value. The k value is kind of small, and we have a significant amount of initial. So initial is large. And so here the initial is large. Here the initial is nothing. The initial is 0. Which is nothing. And so with the simplifying assumption, the math here is going to simplify this. It's just going to be 2x quantity squared. And 1.5 minus x is just going to be about equal to 1.5. And then we'll square that. Now look at the math. I asked you to solve that last algebra, and not many people figured it out. In fact, nobody figured it out. Because it was a bit of a pain. It was tedious to do. But solve this one. This one's going to be a lot easier. This is 4.561 times 10 to the negative 31. It's a lot easier. We just take our 4.561 times 10 to the negative 31 times 1.5 squared divided by 4, and then take the square root of that answer. And I got an x of 5.06513 times 10 to the negative 16. Now compare this to our last calc. The math was a lot easier in this calculation. Oh shoot. All right, what was it?
5.06. 5.1. I guess you could round to 6. 5.16 times 10 to the negative 16.
Was there much of a difference here? No. Barely any difference. To the correct number of sig figs, we get the same answer. To the correct number of sig figs, it's the same answer. So it worked exceptionally well here. And when we calculate this is going to come out to 1.5 bar. This is going to come out to 1.5 bar. And this is going to come out to 5.06513 times 10 to the negative 16 times 2. And so let's double check our k. So I'll do this times 2, square that, divided by 1.5 bar squared, or 1.5 squared. And I get a k value of 4.5610 times 10 to the negative 31, which checks out. Do you see that? But the math was a lot easier. Now, when we do the simplifying assumption, we have to justify it. And so I don't leave it like this because I don't know what the correct answer is. If I don't know what the correct answer is, I can't compare it. Can't compare if you don't know the correct answer. Therefore, we're going to justify it in a circular fashion. If the estimated percent change is less than 5%, then okay. If it's greater than 5%, then it's not okay. So 5% is just some arbitrary cutoff. 5% is already too large. But sometimes the math gets so difficult, we can live with an error that's kind of big. And so let's go ahead and calculate the percent change here. The percent change for us is going to equal the change over the initial. So the change was x, and the initial was 1.5 times 100%. Sometimes the change is 2x, 3x, whatever. But in our case, it's just x over 1.5 times 100%. Our x value was 5.065. I'll just carry 4 digits. 5.065 times 10 to the negative 16 divided by 1.5 times 100. And our percent change came out to 3.37 times 10 to the minus 14%, which is much, much, much smaller than 5%. And so our simplifying assumption worked out well in this case. If the simplifying assumption grows bigger and bigger, then our percent error, we have to worry about that because we're going to get further and further off. All right, let's try out another example calculation here. We're going to look at this reaction in which we're going to take 2 Fe3 plus and oxidize a mercury 1. This reaction is going to produce 2 Fe2 plus 2 mercury 2s. Initial, I'm going to put 0.5 thousand molar Fe3 plus, 0.5 thousand molar mercury 1, and then over here I'm going to put 0.03 thousand molar Fe2 plus and 0.03 thousand molar mercury 2. This is a case C, it's all solutions, no gases. So case C is going to equal, this is given 9.14 times 10 to the minus 6. So what does this favor? Well, the Kc expression, this is going to be the products. So we're going to have the iron 2 plus concentration at equilibrium squared times the mercury 2 plus concentration squared divided by the iron 3 plus concentration squared times the mercury 1 concentration to the first. So what does this favor? 10 to the minus 6, is that going to favor the products or favor the reactants?
Reactants?
Mm-hmm. This favors the reactants. I already have a lot of product here, so we got to ask ourselves, which direction is the change going to go? Is the change going to go forward to make more reactant, or no, to make more products? Or is it going to go backwards to make more reactant? And so which direction is the change going to be? Well, if I had to guess, I'd guess that the reaction is going to go towards the reactants because this ratio is like 1 to a million. But the problem with that is this. We have to be very careful because the numerator is fourth order. The denominator is third order. So it becomes a little bit more tricky because the numerator changes there are going to be more significant. So if we're not sure the direction of the change, how can we figure it out? Well, we can get the direction of the change by calculating Q. So Q is going to be the same as K, except we're going to use the initial concentrations, not the final concentrations. So if I do that, it'll get 0.03 thousand, which is iron 2, and 0.03 thousand, which is the mercury 2. And that's going to be raised to the fourth power. Divided by the concentration of iron 3, which is 0.5 thousand, and the concentration of mercury 1, which is 0.5 thousand. So this is going to be 0.5 thousand squared cubed. So let's go ahead and calculate it. I'm going to go 0.03 to the fourth divided by 0.5 to the third. And I get 6.48 times 10 to the minus 6. When I look at that, 6.48 times 10 to the minus 6 versus 9.14 times 10 to the minus 6, they're actually pretty close. If they're actually pretty close, then that means I'm close to equilibrium. But which one's bigger? 9.14 or 6.48? .14, which means I was guessing this reaction is going to the left because the reactants are favored, but the reaction actually goes to the right. And so the change is going to be to the right since Q is smaller, and so we need to build more product up. So I'm going to fix that here. That is the change. That means I'm going to lose minus 2x molar minus x molar here plus 2x molar plus 2x molar here. And so at equilibrium, I'm going to have 0.5 thousand minus 2x molar, 0.5 thousand minus 1x, or x molar, 2x molar. Oh no, that's not 2x, it's 0.03 thousand plus 2x. And then plug this into the K expression. So on the top I'm going to get 0.03 thousand plus 2x. And I'm going to square that whole thing. Actually, not square it. I'm going to square cube. I'm going to raise this to the fourth power here. Divided by 0.5 thousand minus 2x squared and 0.5 thousand minus x. This has got to equal 9.14 times 10 to the minus 6. So solve for x. So why don't you try to solve this one for x, and give you a few minutes here. Okay, let's. Yeah, why don't you guys try solving this for x, and then we'll come back. We'll talk about this tomorrow. So right now we'll take a break, and then we're going to meet in the computer lab.